What term refers to contraction of the heart? That would be systole. The cardiac cycle creates pressure gradients that maintain blood flow. We'll see a series of pictures. The numbers and timing of each cycle is not that important. But this is for a heart that's going to be beating at 75 beats per minute. And we see that the cardiac cycle begins with all four chambers relaxed. That means diastole, both atrial diastole and ventricular diastole. And when this is taking place, the ventricles are passively filling. Then the atrium contracts, atrial systole, and the ventricles finish filling. Then the atria relax, atrial diastole, and this continues until the start of the next cardiac cycle. So we'll see that the atria will remain relaxed all the way through ventricular contraction. The next step is ventricular systole. The contracting ventricles push the AV valves closed, but this is not enough to open the semilunar valves. This is called isovolumetric contraction. There's no volume change. So the AV valves are closed, but the semilunar valves are not open. Then the second phase of ventricular systole, there's enough pressure to open the semilunar valves and blood leaves the ventricles. Then the ventricles relax, ventricular diastole. The ventricles relax and their pressure drops. Blood in the aorta and pulmonary trunk backflows, which will then close the semilunar valves. At this point, isovolumetric relaxation, all valves are closed, but there's no volume change. Blood is passively entering the atria. And then finally, the ventricular diastole, all chambers are relaxed, AV valves are open, and the ventricles fill approximately to 70% full, passively, as the blood seeps from the atrium to the ventricle.
Welcome to another Anatomy and Physiology Smart Art video, where we guide you through an important piece of art. After watching this video, you should be able to explain the events of the cardiac cycle. Diagrammed here is a single cardiac cycle, which lasts about 800 milliseconds, or 0.8 of a second. Let's begin here at the red arrow labeled Start. In this first image of the heart, all four heart chambers are relaxed, therefore in diastole, and partially filled with blood. Atrial systole, also known as contraction, begins and completes ventricular filling. Notice, the green arrows show the atria contract, and the black arrows indicate blood flowing into the ventricles. Atrial diastole follows and continues until the next cardiac cycle begins. Ventricular systole now begins, and is a process divided into two phases. The first phase, shown in this figure, is isovolumetric contraction. It is called isovolumetric because the volume of blood within the ventricles does not change. During this initial phase, ventricular contraction closes the atrioventricular or AV valves. The second phase is ventricular ejection, when the ventricular pressure finally exceeds the pressure in the arteries, and that pressure increase opens both the aortic and pulmonary semilunar valves. Blood now exits the ventricles and is forced into the aorta and pulmonary trunk. Here, in early ventricular diastole, blood flows backward towards the ventricles as ventricular pressure rapidly drops. This backflow of blood against the semilunar valves causes them to close. At this time, blood is also flowing into the relaxed atria. Notice here, the AV valves are still closed. This phase is called isovolumetric relaxation. Finally, in late ventricular diastole, all chambers are relaxed and filling passively to about 70% of their capacity. To summarize, a single cardiac cycle includes atrial systole, when both atria contract at the same time to complete ventricular filling, followed by ventricular systole. Isovolumetric contraction is the first phase of ventricular systole and causes the AV valves to close, while the second phase is ventricular ejection, which opens the semilunar valve as blood is forced into the artery. As blood pressure rapidly drops in ventricular diastole, the semilunar valves close and the ventricles begin to fill again as all four chambers of the heart rest and passively fill prior to the next cardiac cycle. So what? Why is it important to understand the events of a normal cardiac cycle? Well, this is crucial to understanding many serious heart conditions. For example, suppose a patient has a myocardial infarction, also known as a heart attack, that has seriously weakened the left ventricle. Left ventricular ejection will decrease, blood flow will back up between the left and right sides of the heart, resulting in congestion in the lung. The resulting respiratory complications can be life-threatening. And to understand the many congenital defects of the heart, it's important to grasp the normal cardiac cycle, as these cardiac abnormalities interfere with normal blood flow and valve function.
Pressure change in the aorta during the cardiac cycle. Once the blood flows from the left ventricle through the aortic valve, there's an increase in pressure, of course, in the aorta. And then when that valve closes, there's a drop in pressure, followed by a short pressure rise as the aortic elastic walls recoil. This produces a valley in the pressure tracing called a Dicrotic Notch. And so if you look at the top of this chart, you see atrial diastole, then atrial systole, and then at the same time you've got ventricular diastole, then ventricular systole. And all those different phases of the heart can be followed through this graph here. The heart sounds are officially called lub-dup. Lub is when the AV valves close, and dup is when the semilunar valves close. Cardiac muscle cell contractions are different from skeletal muscle contractions, primarily because of differences in the calcium ion permeability. So with the skeletal muscle, there was a very brief action potential. With the cardiac muscle, it's longer. With the skeletal muscle, the contraction ends when the sarcoplasmic reticulum takes up that calcium ion. And with cardiac muscle, the calcium enters the cells over a very prolonged period. Skeletal muscles have a short refractory period. Cardiac muscles have a longer one. And so this is showing a skeletal muscle fiber action potential and contraction. This is a cardiac muscle cell action potential and contraction, so it's much more prolonged. And this is because calcium is entering the cell over an extended period of time, and that maintains the stimulation. There are 3 stages of a cardiac muscle action potential. Those 3 stages are rapid depolarization, plateau, and repolarization. So I don't know if you remember anything from the muscle chapter, but the membranes are at resting potential, and that's usually like -70 millivolts. And as ions flow across the membrane, that potential increases to a certain point. So we'll see what happens during each of these stages of the cardiac muscle action potential. So with rapid depolarization, it's similar to that of the skeletal muscle. At threshold, the voltage-gated sodium channels open. So there's a massive flow of sodium ions into the cell. Channels open quickly and briefly, so it's very, very fast. With the plateau, the sodium channels close, and the cell will actively get rid of that sodium. It will pump it out. But then other channels, calcium channels, open, and they allow calcium to flow in more slowly. This causes a longer plateau. Then those slow calcium channels close, and potassium channels open. So potassium rushes out, and this causes a rapid repolarization, and it restores the resting potential. Which of the following is not a layer of the wall of the heart? Parietal pericardium. What channels in the cardiac cell membrane open to create the plateau? That's the second step. And that would be slow calcium channels. So there are electrical events in pacemaker cells and conducting cells that establish the heart rate. So we want to talk a little bit about cardiac output. And cardiac output is a combination of the amount pumped per minute and the how many beats per minute, the heart rate. So the cardiac output, the actual definition is the amount of blood pumped from the left ventricle every minute. So the typical heart beats 70 times a minute. With each beat, the heart pumps 60 to 90 millimeters, which is 2 to 3 ounces. 4 ounces is a half a cup. So this is less than a half a cup of blood. It can move 5 to 7 liters of blood in 1 minute, 7,600 liters or 2,000 gallons per day. In a lifetime, it beats over 2.5 billion times and pumps over 2 million liters or quarts of blood. So cardiac output is equal to heart rate, the number of contractions per minute, which is probably 60 to 70 to 80 for all of you, times the stroke volume, the volume of blood. By changing either the heart rate or the stroke volume, you're going to change cardiac output. Cardiac muscle cells can contract on their own. This is called autorhythmicity. There is a conducting system, and we will look in detail at that conducting system. And these are specialized cardiac muscle cells, not nervous cells. And below there are the components of the conducting system. It begins with our own personal pacemaker, the SA node, or sinoatrial node. And then it follows to the internodal pathways, the AV node, the AV bundle and bundle branches, and finally the Purkinje fibers.